And okay, so in this talk, actually, we'll be revisiting issues about regret, price of anarchy, and different classes of equilibria, like Nash equilibria, correlated equilibria, coarse correlated equilibria. But once again, we'll be doing this from our own novel perspective of dynamical systems. Okay, and we'll be gaining some like new, and I would say somewhat surprising insights about what these concepts mean and imply. Okay, so this part of the talk actually will be roughly half and half. So the first half of the talk would be almost like, you know, classical knowledge that in the price of anarchy, robustness frameworks, and so on and so forth, and even like, you know, just seeing the formal definitions of different equilibrium concepts. So hopefully, you know, for most of you, maybe this is well known, but like maybe for some of the newcomers or some of the participants from the other workshop, this will be useful. Okay, but the second part of the talk is actually going to be brand new. So it's going to be results that come by putting in this classical framework together with, again, with a dynamical system perspective. So what happens if you take price of anarchy, correlated equilibria, you know, yeah, and you put them together with chaos? Like, how do these things even make sense together? Okay, and I think we'll see that there's some rather counterintuitive things emerging. All right, so let's go to the easy part. So, you know, Kosti, Vasily, you can sleep now, and then I'll let you in when the new stuff arises. Okay, all right, so here's the definition of congestion games. All right, so this is the, okay, this is arguably one of the most well-known class of games, arguably maybe the most well-known outside the zero-sum games. So these are games that you can think of this as roughly trying to model traffic routing. Okay, so this is the atomic case. So you have like a discrete number of agents n, and you have a number of resources or edges, and each strategy corresponds to a set of resources, typically, although not necessarily, a path in some sort of like network. And each edge has a cost that determines its cost as a function of the number of people that are using it. So think of the delay of going through that edge that is, let's say, strictly increasing as more agents pile on it. And the cost experienced by a player is just the sum of the edge costs. Okay, so here's an example. So I have a red player and a green player. The red player has these two strategies available, like this path and this path. He wants to go from this source to this destination node. Similarly, the green agent wants to go from this to this destination node. And let's say here's the strategy profile. So the cost for the red agent is 1 along the first edge, then +2, +2, +1 equals to 6. And the cost for the green agent is like 2 + 2 + 2 + 2 equals 8. Okay, so that's a configuration. And then a motivating example that's useful to keep in mind is the simplest possible, in some sense, special case where you have, let's say, n players and n parallel links. Each of them have a cost equal to x. Okay, so all right, so these games are also known as balls and beans games, because you can think the players as being balls, and then you choose your bean, and your cost is the number of other balls which are like in the same bin as you. All right, so, and okay, there's a reason why potential games are like, you know, hold such a special place in game theory, congestion games, sorry. And the reason is that they're effectively isomorphic with another very important class of games, which are known as potential games. So potential games are games that have that come up with a single function phi, such that when you have exactly one agent deviating from any given configuration, so everybody else stays as is, and I deviate from some strategy to another to SI prime, okay, then the difference in my utility is captured exactly by the difference between the potential function between the same two outcomes. Okay, and why is this very important? Because of course now, okay, so what is not clear at all, but just take believe me for this, is that like the congestion games that we saw on the previous slide, they have a simply actually computable such potential function, right? And the opposite direction is also true, which is even more surprising, So for every such potential game, if you give me such a potential game, I can actually construct a congestion game from the previous slide that are isomorphic. Okay, so this means like both agents in both games, you have the same number of agents, same strategies, and for every configuration is you have the same utilities. Okay, all right. The reason why we like these games is because every, let's say, local maximum or local minimum, depending on if it's a cost of a utility game, is a NAS equilibrium, and that's clearly, and also like every sort of like best response path, and actually more general learning dynamics, like they act as a Lyapunov on the potential, which let's say strictly decreases up until the system equilibrates. Okay, so this is the prototype of equilibrating games. Okay, and as I said, like, okay, here's the other class of games, of course, are very important, which are like zero-sum games. Of course, we all know this. We all know the definition of NAS. Okay, every player has a profitable product of mixed strategies. Okay, right, and then somehow like we meet already one of the most important problems in game theory, this equilibrium selection process problem. And this is like, okay, unless you're playing a trivia, like a game like zero-sum game, which has a well-defined utility for all NAS equilibria, so effectively unique solution. Like in these games, you have two different NAS equilibria, and these equilibria can be quite distinct, okay, in terms of, let's say, the social welfare, the sum of the utilities of the agents, and so on and so forth. So which NAS should one choose? Okay, this is actually, as I said, like a deep question. And Koutsoukias and Papadimitriou back in now more than 20 years ago, they came up with a fundamental idea that says like, okay, just do worst case analysis. So if many equilibria exist, just take the worst. Okay, and then the hope is that like if you look at the social cost, which let's say the sum of the agents' costs at this worst case equilibrium, then this worst case equilibrium won't be, or clearly its cost will be worse than the cost of the optimum state. Okay, but maybe it won't be too much worse off. Okay, and if it's not too much worse off, then maybe we don't really care about which equilibrium gets selected. All of them are roughly equally good. Okay, so that's the idea. What's much less clear is that like this idea has any sort of like legs to walk on. Here's an example of a congestion game. So you have 10 agents, and they all want to go from point A to point D. And I claim here, right, so the NAS equilibrium has all of the agents going through this zigzag path, and then they have a delay of 20. But if you were to split yourself like 50-50, so 5 agents above and 5 agents below, you have a cost of 5 and 10, 15. Okay, so this ratio, this price of anarchy for the simple, and that's actually a unique equilibrium. So the price of anarchy for this, let's say unique pure, the price of anarchy for this game is 4/3. Okay. Okay, so and this is like a relatively simple network. Okay, so what is really amazing is that Koutsoukias and Christodoulou, again, almost 20 years ago, like they proved that, okay, forget about this very simple network, create a crazy big network, like, 1 billion edges, like 1 million users, like put whatever you want, but linear delays, okay? Then the price of anarchy cannot be too much worse than 4/3. Actually, it would be at most 5/2, okay? So that was a fundamental idea. And then actually, Ralph Garden came back in 2009, and he developed like a way to systematize all of these proofs in a framework that's known as the Lambdamishmos Framework. What's the idea here is that, well, suppose you have a game, and then I don't tell you how, but suppose that you can prove this property for this game. So take any two configurations, strategy profiles S and S prime, and then you want to have this. You want to have this inequality being satisfied. So here you have the summation of the cost of all agents, where the agent I chooses outcomes from the first, let's see, from the second, excuse me, profile, and everybody else chooses from the first. And then this is the social cost in these two states. like as long as this is satisfied, then immediately this results the following price of anarchy bound, lambda over 1 minus mu. Okay, and the proof, okay, which what Ralph Gardner understood is that like that was a way to rewrite the proof by the initial proof by Koutsipras and Christodoulou, just follows from these 3 lines. Okay, so the first line is just the definition of the social cost. The social cost is just the summation of the cost of all users. The second line is just an mass equilibrium. Well, you know, I'm at so if S is an mass equilibrium, then if I deviate, my cost can only increase. And then the last line just comes from the definition of Lambdamishmos smoothness. Okay, and then just rearranging. Okay, remember, S is an mass equilibrium, and S prime could be the optimum state. Okay, can be for any state. Okay, so just by rearranging, you get the price of anarchy of lambda over 1 minus mu. And particularly the case of linear congestion games is just a specific instantiation of this more general technique for the case where lambda and mu have these 2 constants. Okay, 5 over 3, 1 over 3. All right. Yeah, let me know if you have any questions at any point. Okay, of course, we're not done. Pure Nash equilibria are even harder to compute than mixed Nash. And we have like a bunch of like really hardness results here by Kostis and friends. And then there are also other hard problems, communication complexity. And even if these 2 problems are not hard enough, you know, you can definitely have even in very simple games like zero-sum games, agent behavior not converging. Okay, so a lot of problems. You cannot expect to guarantee equilibration and pure Nash equilibration. So, you know, we'll go to our favorite pair of slides. Okay, just do not regret. We know how to do that. And yeah, so, okay. This is my cartoon slides, okay? We went over them in the previous talk. And we know how to do it. And then we know how to do it. So here's like the prototypical algorithm, multiplicative weight updates. You know, as long as you use, let's say, some decreasing sequence of step sizes, particularly 1 over square root of t, you get square root of t aggregated grid, right? And as we said, like if you're willing to you know, consider the case of continuous times, you can actually get constant regret. So all good. So this no regret properties, it's actually guaranteed for free. Okay. All right. So what do no regret properties buy us from the perspective of equilibration? Okay. So we have this notion of Nash equilibrium. And here what I did is I've actually reformulated the definition a little bit. I give it in a kind of like artificial way. So I say Nash equilibrium is a probability distribution over outcomes that is also a product of mixed strategies, okay, that it's equal to the product of its marginals, such that no agent has a profitable deviating strategy. Okay, now I'm going to remove, okay, so that's of course the Nash equilibrium. Now I'm going to remove the restriction that this probability distribution over the outcomes has to be a product. Okay, if I just do that, the simple like somehow removal, now you have a different equilibrium concept altogether. So clearly that's a relaxation, right? So just to remove the constraint, so the set can only get larger, right? And that's what we call by coarse correlated equilibrium. Okay, and just to give you an example, okay, of a coarse correlated equilibrium in practice, okay, here's such a distribution. Here's a distribution that chooses uniformly each of these 3 outcomes. Okay, so the first rock probability third, paper probability third, and scissors probability third, right? And now I claim that no player has a deviating strategy. Why is that the case? Well, look, let's do the row player. In expectation, I get 0. Okay, and now suppose I deviate and let's say I play rock with probability 1. Then what's my new expected utility? Well, my opponent, somebody asked about this question in the previous talk. My opponent does not change his distribution. So my opponent's marginals stay invariant. So my opponent will play 1/3 of the time rock, 1/3 of the time paper, 1/3 of the time scissors. Okay, but now I'm playing rock with probability 1. But my expected utility is still 0. So I cannot deviate and improve my utility, right? And the same for paper and the same for scissors. Okay, so this this is the distribution satisfy the definition that I gave you, so it's a Cosquad equilibrium. Okay, and now there's a thing in between. The thing in between is called the correlate equilibrium. Okay, and now it's a restriction on the set of Nash, on the set of correlate equilibria, of Cosquad equilibria, and it's the following restriction: is that like now I require that no agent has a profitable deviating strategy, even if the player is allowed to deviate after receiving the advice from the joint distribution. Okay, so just that is anyone okay? Can someone see why this is this a correlate equilibrium? No. Okay, correct. Why? Because suppose I received the advice, let's say, of I'm asked to play rock by the distribution. Well, now I can condition on this information. Okay, so condition on this information that I was told to play rock. I know that my opponent plays rock with probability 1, but if my opponent plays rock with probability 1, then I can do much better, right? I can just play paper. Okay, so this is a case where I have something that is a Cosquad equilibrium, but it's not a correlate equilibrium. Okay, and that's it. That's our universe of and just one last thing, if it's not obvious, that like every correlate equilibrium is every Nash equilibrium is trivially a correlate equilibrium, right? There's no way to, since the distribution is a product, there's no way somehow to take any advantage by being given some information, right? So this is our universe. Okay, pure Nash equilibria, which are only guaranteed to exist in very special games like potential games or congestion games, mixed Nash equilibria, which are guaranteed to exist in all games, but they're computationally hard, and then correlate equilibria and Cosquad equilibria, which are much easier to compute both in a centralized and a decentralized way. Okay, all right, that's all good. All right, so no regret and correlate equilibria and Cosquad equilibria, sorry, they have a very intimate connection. Well, effectively they're like one and the same. Like okay, let's look at this sentence. A history of non-regret algorithms is a sequence of outcomes such that no agent has a single deviating action that can increase your average payoff. Okay, this is by the definition of regret, right? So regret means that like no single player can play, let's say, can deviate to some fixed action with hindsight and do something better. Okay, and then because we're okay with sublinear regret, we're talking about average payoff. Okay, so this is the definition of a sequence of no-regret outcomes. Here's the definition of a Cosquad equilibrium. It's just a probability distribution now. It's not a sequence over time, just probability distribution over outcomes such that exactly the same thing. No agent has a single deviating action that can increase your expected payoff. Okay, so it's almost like here proved by pointing words like on the slide. Like if you take a history of no-regret outcomes and you create a distribution that just samples like one of the first 3 outcomes uniformly at random, as t goes to infinity, this distribution is bound to converge to the set of Cosquad equilibrium. Okay. All right. Hopefully this should be clear. All right. Okay. And the very nice property here is that the proofs that we saw that developed by Ravkarden with a Lambdamishmos smoothness, they actually immediately extend from the bottom, the bottommost equilibrium solution concept, which is the pure Nash equilibria, all the way to the top, to the set of Cosquad equilibria. Okay, and remember, okay, so this is the proof that we went through the 3 lines together. So this comes from the definition of social cost. This comes from the definition of pure Nash equilibria. This comes from the smoothness. Okay, and here's the proof, how the proof goes for Cosquad equilibria. Effectively, it's it's the same, it's just using linearity of expectation. The only thing, so the only thing here that in some sense you have to check is that like that this inequality here exactly captures the fact that this this state S is chosen according to the probability distribution that is a Cosquad equilibrium. Okay, So that's the very definition, right? So the very definition says that, like, okay, if S is chosen to according to a Cosquad Equilibrium, then if an agent just deviates and say, like, no, forget about the advice coming from the distribution, I'm just going to play this SI star for all time. Okay, then you're only going to penalize yourself. Okay, so the cost would only increase, and everything else is just linearity of expectation. Okay, so this amazing somehow, like, inside that if you rewrite the proof somehow in a very specific structure, then this generalization somehow, like, follows immediately. Okay, so all right, so this is somehow like where we are, right? So we have and then I've added like one other layer of solution concept, which is like all the way at the top, and we say, like, okay, look, we have Q-NAS equilibria, NAS correlate equilibria, Cosquad equilibria, and then all of these equilibrium solution concepts satisfy this notion of the price of anarchy is within a lambda over 1 minus mu of the social cost of the optimal state. Okay. All right, so now what we're gonna try to explore is to show somehow, like, okay, as I said, try to create a kind of connection between this kind of classically known statements and things coming from things inspired, at least to some extent, by dynamical system interpretation of learning games. Okay, and we'll see that, like, maybe there are some somehow like caveats or weaknesses in the framework that possibly open up opportunities for, like, future work, particularly within the semester. Okay, so there's a lot. Okay, so there's a lot happening here on the slide. So there's 5 different. So here I give 1 to 5 for the 5 solution concepts in the sorry. So 1 to 5 for this. So 1 is the top layer, 2 is Cosquad equilibrium, 3 correlated, 4 mixed NAS, 5 pure NAS. Okay, and I will make 5 different statements of different level of maybe surprisal that I will show that are formally true. Okay. So first of all, about lambda mu approximately optimal states. Well, in some sense, in some games, these states can be rather weak, in the sense that, like, all agents, although the states are approximately optimal, all agents may be strictly worse in stat states in terms of experiencing higher cost, strictly higher cost than their min-max cost. Okay. So min-max cost is what I can guarantee myself. Like, if I just try to minimize, so this is like an absolutely minimum guarantee, right? So I'm playing for myself, trying to minimize my cost. Everybody somehow is trying to gang up on me. Okay. And I'm saying that, like, in approximately optimal states, it could be the case that no single agent can actually guarantee this min-max failure. They can all be doing strictly worse. Okay. So there are states, there are games where approximate optimality is not hard, is not, let's say, very useful as a concept. Number 2, this is actually, I think, rather surprising. It says that, like, look, there exist no regret algorithms in smooth games. Okay, actually, let's say congestion games, linear congestion games, such that the sequence of no regret algorithms play only strictly dominant strategies. Okay, so and by strictly dominant strategies, I'm using the most powerful definition. So these are pure strategies which are strictly dominated by another pure strategy. Okay, so this is just something that, like, okay, immediately you look at this, you compare it with any other, yeah. So it would be something like this. All right, so my utility here is, let's say this is a utility game. This is 1, and this is 1. And 1. This is 2, and this is 3, and this is 4. Okay, so this is strictly greater than this. This is strictly greater than this. Okay, so this is strictly dominated. But all players will only play these strategies in the whole history. Okay. All right. So no regret can actually lead to, rather, if you prove nothing else, Okay, if you don't understand, let's say, maybe more about the topology of the orbits, like it could be that no regret is rather weak, even in smooth games. Okay, and I will prove this actually both in congestion. So this is for different classes, let's say, of smooth games, both for congestion games and valid utility games, for those who are like know these things. Okay, but now, okay, we say like, okay, Cosquad Equilibrium can be really weird. What about, okay, we can get correlated equilibrium almost for free. Maybe we're good. Okay, well, not quite. Okay, so we'll show that it's possible that exist correlated equilibria which are actually selected by replicator dynamics. Remember, this is an algorithm that has constant regret. Okay, and these are like in very simple games, in trivial games, and these correlated equilibria are formally chaotic. So if you try to predict the sequence of what we play next, it's impossible. Okay, so this will be on some sort of like strange attractor. The correlated equilibrium support will be on a strange attractor on the game. Okay. Number 4 is like, okay, look, all right, Cosquad Equilibrium can be pretty weird. Correlated equilibria can be pretty weird. Well, let's go for Nash. Okay, now Manoli is here. Will be like, yeah, this is our paper. That's right, Manoli. Like then, oh, actually, this is a relatively unknown but very strong and counterintuitive result that says all mixed Nash equilibria, even partially mixed, in every game, okay, in every game, are not even locally asymptotically attracting for all FTRL dynamics. So take FTRL algorithms, which have low regret, and put them in continuous time. So now they're supercharged. They have constant regret. Okay, and I'm saying like, okay, this is the best we can do for regret. The best thing I have to do is do some sort of like discretization magic and get the same performance in discrete time. And I'm saying like, okay, forget about discretization tricks. Like go for the easy case. Okay, and now give them the simplest possible problem. Okay, find a mixed Nash equilibrium, and I'm saying like, forget about PPAD hardness. Forget about starting in some weird part of the state space. I'm going to get arbitrarily close as you want. Go to the 2 to the minus 50 ball for the Nash equilibrium. And all I'm asking from the algorithm is to do the last step. Okay, just, it's there. Go. No. Not a single game, not a single mixed Nash equilibrium, not a single FTL dynamics can give you this. Who knows? No. It could be doing, maybe cycling, maybe it goes away. But one thing that will not happen is this. Is the thing that we want. Okay? No, never. Okay, this is what you want, right?
It's for some initial starting point.
So for any, okay, so here's the statement again. I mean, I will go into details. Okay, so I have a specific slide for each of them. So let me go through and not go through the specifics one time. And last but not least, okay, now I'm going all the way down to the bottom, rock bottom. Okay, pure Nash. And I will prove something that I claim is rather counterintuitive. Okay, that the pure price of anarchy of affine congestion games is unbounded. Now you say like, okay, wait. What? Oh, it's the price of anarchy over the worst pure Nash. Okay. All right. Remember, like the result I claimed with okay, we have to revisit that slide. Okay, but we saw a result, you know, by Christodoulou and Koutsoukias, and then the follow-up by Raf Garden, and said like, in the case of linear congestion games, okay, price of anarchy is 5/2. I'll say if you go from linear to affine, it's unbounded. Okay, let's go to one of these points one at a time. Okay. All right. So then, okay, arguably, okay, this is something that here's a property that, okay, here's the simplest possible game: 2 balls, 2 beans. Okay. And then, as I said, like this is a linear congestion game. It's arguably a very, very simple one. So we know what the price of anarchy for all of them is 2.5. All right. But here's the case. Like for this game, it's impossible actually to create any state, let alone an equilibrium state, with factor more than 2 from opt. Okay. So here, like, okay, like the 2.5 is just a trivial statement. Okay. But you see, like, okay, maybe this is just, okay, this is just a small example, but it already shows you something weird, right? That you have some guarantees. And for the game, if you really care about this game, you don't really know anything, given the approximate optimality guarantees. Okay. But now, can this happen over large classes? The answer is yes. Okay. So here's my favorite example: n balls and beans. Okay. Go and choose any arbitrary n. Okay. Now that's a class of games. Okay. Again, it's a linear congestion game. So again, we know the robust price of anarchy is 2/5. Okay. And at optimum, this is trivial. That's why the example is chosen. The optimum has like all agents pay a price of 1, right? But now, what is the safety? What's the min-max value for the agents in this case? Well, the min-max strategy, this just by symmetry, you have like, you know, each player, the player chooses uniformly at random a strategy, like 1/n. And then it doesn't matter if everybody else tries to bang up on you, right? So if you play, so I'm the one guy, I'm trying to play defensively, unpredictably, 1/n. Okay. And now let's see, even if all of the other players, let's say, use this, use the first machine, then what's my cost? Well, with probability n minus 1/n, I'm just by myself. So I just pay a cost of 1, right? And then with probability 1/n, well, now everybody like, you know, is on the same bin with me. So I have the maximum cost of n. Okay, so, but that's 1, and that is 1 minus 1/n. So this is 2 minus 1/n. Okay. And nothing else, nothing worse can happen to you. So just by min max, I know that I should not be paying more than 2. So the min max price of anarchy is less than 2. Okay. But this is strictly less than the robust price of anarchy. So for these games, like even if it doesn't matter how fast the grid goes to 0, we don't know anything more than what we knew, you know, using like the Blackwell's like min-max results. Okay. So approximate optimality in some class of games could be rather weak, and there we need something more. Okay, maybe we need like we need something more. Okay, and here's something interesting. In no-regret games, okay, in smooth games, it can be the case that all agents play strictly dominant strategies. Okay, how's that possible? How's that possible? It feels like counterintuitive, right? So here's a simple example. So we have like 2 agents and 4 available paths. So the paths, you have all the agents need to go from point A to point D. Yes.
There's a question by Eva.
Yes.
Hey, sorry to chime in. Any chance you're willing to go back to your previous example?
Yes.
Like the price of energy on this particular example of a game is not actually 2.5, or I don't think it is.
Right,
Like
right.
it's a concrete
Right.
game. The worst case is that, but this is not the worst case, right?
Yeah, that's a great point, Eva. Here's what I'm saying, right? Suppose, okay, of course, the price of anarchy for this game is going to be much smaller than 2.5. But for me, but suppose all you know is you have the n players and you use regret minimizing algorithms. So like the first one uses FTRL with Euclidean regularizer. The second is like FTRL. The third one is regret matching. The fourth one is whatever you want. Okay. So now nobody has analyzed this combination of non-regret algorithms. So we don't know that they converge to Nash. So all that we know is that the regret goes to 0. Okay. And I'm saying like, if that's all we know, then for this specific game, there's nothing. The only price of anarchy result that I know that we can apply is 2.5.
But do you know an example on a concrete game where there is a high cost course correlated equilibrium and yet the minimax value is lower?
Sorry, can you repeat that, Eva?
I mean, I'm just wondering if there really is an example on a concrete game which has a high cost course correlated equilibrium and that, you know, with a low cost min-max cost.
Yeah, I mean, this would be such an example, right?
No, it's not, because I don't, where is the course correlated equilibrium that's costing so high?
Okay, so
Is
here
everyone-
you have like the mixed NAS. Okay, so the problem, right? Right. I mean, maybe okay, Eva, because let's return like let's have this question session maybe at the end.
Okay, fine, sorry.
No,
That's
but
fine.
thank you. No, I'll be very I'll be very much willing to have this discussion. But actually, I don't think it's the most interesting result, so that's why I want to proceed. Okay. All right. So here's the statement now. I'm going to say that like it could be the case that you have like a bunch of no-regret algorithms, and your regret could be actually constant, and you can have a smooth game. And this type of no-regret algorithms could actually be playing only strictly dominant strategies. All right. So here's an example that's a linear congestion game. Okay, just two agents. They want to go from point A to point D. Okay, and they have like 4 available paths. So this, and this. Okay, so clearly I've added some like superfluous paths. So this is strictly dominated by this, and this is strictly dominated by this. Okay, all right. So now I claim, let's take this distribution. With 50% probability, the first agent uses this path here, and the other. So both players use the strictly dominant paths, but they alternate. With 50% probability, you have this pair. With 50% probability, you have the other pair. Okay. So I'm going to claim that like this is actually course correlated equilibrium. All right, let's see this. So what's the cost for any player? So everything is symmetric. So the cost for any player here is so it's 0.1 and 1. Okay, so it's 1.1. All right. And similarly for the other player. Okay. Now let's see what will happen if they deviate. So clearly, the only thing that can deviate is symmetric is to use, let's say, this path, ABD, ABD. Okay, here they pay a cost of 1. Okay, but here, let's say, let's choose the deviating agent. So the deviating agent, let's say, is the red agent. Okay, so the deviating agent will play ABD in both graphs. In the first graph, he pays cost of 1. In the second graph, however, he pays cost of 2. So in average, it's 3.2 is 1.5. So that's strictly higher than 1.1. So actually, this is a state that has negative regret for all agents. Okay. All right. And this is just a smooth game. Okay. Now the thing is that like, okay, you can say like, okay, this is like a really weird example. Like I'm sure no-regret learning algorithms would never find this. Okay. But unfortunately, due to some work we've done with Eva actually, and some follow-up work with my student, Barnabe, we can actually construct no-regret algorithms that for any arbitrary game, they can reproduce as the unique somehow time average any course correlated equilibrium of our choice, no matter how irrational they are. Okay. Putting these both results together, okay, there exist no-regret algorithms such that in smooth games, only strictly dominated strategies are played by all agents. Okay. And here's the intuitively the idea behind this no-regret algorithms. So this algorithm do the following. So like, okay, well, so let's say me and Kostis, and like we're gonna agree to try to simulate this weird equilibrium with the two agents. Okay, so I play this, you play that. Odd games, odd days we do this, even days we do that. Okay. The first time somebody deviates, we just say like, oh, forget our agreement. Just play multiplicative weight updates with decreasing step sizes, and that's it. This result in this specific case will never deviate. and will converge to the Cosquad equilibrium of our choice, even if it's very unnatural. In any other game, like immediately it doesn't matter if immediately or not, like you cannot accrue regret. Okay, so your total regret remains bounded, and you converge to this very unnatural behavior. Okay, now admittedly, these are like super weird dynamics. Like no dynamic that any human being that's not a theoretical computer scientist that has to create artificial counterexamples would have this kind of behavior. Okay, but this is important to know, because this says something about theoretical papers. That if your theoretical paper does analysis of algorithms using regret alone, then you cannot guarantee that you cannot have this behavior. You need to prove something more. Okay, and this is not just for congestion games, but also effectively the same example applies for the other, let's say for valid utility games, and quite possibly for other smooth games as well. So I haven't tried to be exhaustive here, okay? But both of these two well-known classes of games, they have this weakness. Yes.
Do you believe that the FTRL type no regret algorithms can converge to really bad course correlation?
We'll go. Great. Thank you, Yannis. It's almost like thank you for this.
Not a big.
Yes, no, but like I will go to this right now.
Okay, cool.
All right.
You didn't pay me.
All right, thanks. All right. I doubly appreciate it. Okay. All right. So so Yannis says, okay, what about really good, very natural no regret algorithms? Well, you know what's my candidate of choice? Replicator. Okay. So replicators for me is the echelon. Is that the thing I'm trying to replicate in discrete time and just get it very quickly in continuous time. Okay. So here's the thing. With replicator, you can effectively, even in normal form games, okay, orbits of replicator dynamics in normal form games, even with just two agents, can be arbitrarily complex. And what I'm saying here is that by arbitrarily complex, here we have like a target dynamical system. This is like a well-known formally chaotic system, what's known the Chua system. Okay, we have a mechanistic process, an algorithm that tells you, okay, I'm going to try to simulate this process using replicator. Okay, give me a game and an initial condition so that these two orbits are formally similarly close. Okay, and you can do this. So you can formally create actually simple two-player games. Simple. Large, you need a high dimensionality. Okay, whose orbits are this? So this is actually a replicator orbit. Okay, so you can actually compute the regret of this. The regret of this could be like total regret would be something like 5. Okay, doesn't look like it, but this is a perfect CCE. Okay, and I can say like, okay, CCEs can be very bad. What about correlated equilibria? Maybe that's our way out. We know how to do reductions, okay, almost for free from CCE to CE to correlated equilibria. Okay, is it the case that correlated equilibria are good? The answer is no. Okay, you can create. Okay, instead of using, let's say, 2 players and a lot of strategies to get flexibility from the strategies, just use several agents, but only 2 strategies for each. And if players have only 2 strategies, then course-correlated equilibria and correlated equilibria coincide. Okay, this is an attractor in a 6-player 2-strategy game, which is actually formally chaotic. Okay, this is like a strange attractor. So this actually leverages some result in dynamical system theory, but this is actually formal chaos. Okay, so correlated equilibria, which are like naturally selected, can be formally chaotic. Okay, even in games with 6 agents, 2 strategies, normal form games. All right. So, yes.
Is this an example, or you have a
example?
To,
this is an example. This is just an example. Correct.
How about the previous slide?
The previous slide is a procedure, actually. Yeah.
Okay. So what is the input for the procedure? What's the output?
Oh, okay. So, yeah. So the input for the procedure is effectively the vector field of an OD. Okay. And then the output of the procedure is a payoff matrix and an initial condition such that the all bits of the dynamical systems are approximately similar. So I would say like, okay, there's some approximation error, okay, but for some specific versions of the proofs, there's no approximation error. And you can leverage the special cases to prove formal case.
So I give you what kind of ODE I can give you as input? Like I give you, I literally write down for you an ODE of my choice.
So we need, okay, so we have some restrictions. So the paper here is published on Cold. So we have some restrictions on the allowable. So you need the state space to be homeomorphic to some simplex. But other than this constraint, you're good.
Like, so you're saying that it's a natural algorithm. So is there any no regret learning algorithm that does not have this kind of behavior?
I don't know. Yeah. Like, I mean, yeah, so that's a great question. Now you can say like, okay, look, maybe Replicator is really, really weird. Okay. Maybe. And maybe somehow.
Can you repeat the question?
Yeah, okay, sure. So the question is like, okay, is there some no regret algorithm that doesn't have these peculiarities? Okay. And I'm saying like, yeah, I don't know. I mean, I think it's already, I was surprised that you can actually do this at all with any algorithm, right? And I don't even know how to prove a negation of this result.
If there is some kind of learning algorithm that doesn't have chaos in any.
Correct. Yes. Okay. Yes, correct.
So, it might also be about the game, right? So
It is very much about the game.
yeah, if you have something like a potential game,
Yes.
I do not expect this behavior.
Oh, yeah, of course.
Yeah.
Yes.
So it's not only about the dynamics; it's also about the game you try to simulate.
Oh, 100%. Oh, 100%.
Yeah.
So all I'm saying here is that, like, I can give you today, I can give you the numbers of a 6-player 2-strategy game, and I can say, like, okay, go and simulate this, and you'll see this. Okay. I can see the code. So okay.
So the red stuff are what exactly?
So like
Continuations?
no, these are this is an attractor. These are different initial conditions.
Okay.
And this is somehow like that needs. Okay, I don't want to go into technicalities because this is not formally an attractor. It's a low-dimensional attractor. So this is a little bit hidden. So it is. So there's the infinite number of initial conditions that converge to this point, but not an open set. Okay. So yeah. So these things are not okay. That's the other thing that's important to point out. So these dynamical system behavior can actually be hidden, and all of them by construction are hidden in a low-dimensional zero-measure set of the dynamics. So it could very well be the case that if I'm not there to give you the hint and say, "Oh, look, the chaos is there," that you never find it. Okay. So, but then, because again, this is in some sense this is a hardness result, right? It's a construction. I hide like a very complex dynamic between something that could be somehow like not complex at a high level. Okay. All right. So Cosquad Equilibrium can be strands. Okay. What about moving further down? Okay. What about mixed nuts? Okay, mixed nuts cannot be strange. Okay. Like mixed nuts is just the point. For topology, it doesn't get any simpler than this. Okay. But now here's the question. Okay, and here's like something that I was thinking about. Okay, suppose to say, at the end of the semester, we're going to write a book on learning in games. We did it. We did all the cool stuff. And of course, it would be nice for the cover of the book to have some dynamic. Let's say they follow the little dynamics such that they converge to Nash. Okay, here's a Nash. All the things converge there, like maybe spiraling, maybe direct convergence. That would be a really cool picture. Well, here's one idea, like just choose a strict Nash. Well, strict Nash is kind of like cheating, in some sense, like, okay, if you get super close to a strict Nash, then in some sense it's a dominant strategy in that neighborhood. Of course, everything will converge to that point. Well, what about something that's not a strict Nash? What's something that's partially mixed? It's impossible. This comes like purely from dynamical systems theory. Okay, in some sense, to be able to do this, you need to have something of positive measure that shrinks. Okay, So you have some ball of initial condition that contracts, and vanishes into the equilibrium point. And these dynamics actually do not allow for this. Actually, we'll see this tomorrow, why technically this is true, okay? But due to this result, okay, I mean, I find this to be somehow a stunning critique from online, from FTR dynamics for mixed NAS. Economists would say like, okay, mixed NAS are everything, are a solution, again, are the perfect solution. And FTRL, you put it there within computer accuracy, and you say like, okay, do it. And they won't, never, again. I think that, I mean, I don't know what this tells me. Maybe, okay, maybe now you say like, okay, maybe we've been thinking about dynamics wrong, really wrong. Okay, maybe we really need optimism for example. Yes. So optimism can actually solve this. Right. But optimism, the way you can actually prove the following. So optimism is volume shrinking in zero-sum games, but it pays a price in coordination games. So in coordination games, it becomes volume expanding, and it becomes chaotic, actually. So the interesting question here is like, okay, can you find the dynamic that actually works? Okay. Yeah. Yes.
That's for a discussion, but in the case that in the payoff that you get, there is a noise. Even optimism does not work well. The optimism and the extra gradient tricks that we apply.
Okay, Manoli, sorry, but I'm gonna take over now.
Oh, yeah.
Let's have discussion.
Yeah.
All right. Yeah. Okay. Last 5 minutes. Okay. I said the best for last. Again, I claim the pure price of anarchy of affine congestion games is unbounded. It's infinite. Again. All right. Proof by example. Oh, okay. There we go. Proof by example. Okay. So here's my game. Again, 2 by 2. So first of all, like, okay, this is not a congestion game. It's just a simple game. It's a cost game. Again. So high is bad. So this game has clearly two pure NAS equilibria, the AB and the AB and BA. Okay. So of course the price of anarchy, the pure price of anarchy is exactly W, right? So this is the optimum state. I mean, this is still an equilibrium. This ratio is W. Okay. And W, of course, can be anything. It's some positive number. So the supremum over this family of games of price of anarchy is infinite. Okay. But now I'm already saying like, okay, you should already be starting to worry. Here's the issue. Then like this is clearly a potential game, right? It's a potential, okay, it's a potential game because all players have the same payoff. So the potential is just a common payoff, right? And by this isomorphism between potential games and congestion games, there should be a congestion game that's isomorphic. Okay, so let's construct this. Okay, so here, so there's two agents, the row agent and the column agent. Okay, and there are 4 congested elements. AA, AB, BA, BB. Okay, and the row agent has these two, so there are 4 elements, 1, 2, 3, 4. The A strategy for the row element contains these 2 sets, these 2, the B, these 2, and then for the column agent is these 2 and these 2. Okay. And here's the costs. With load of 1, the cost of all of these congested elements is 0. With load of 2, the cost is exactly what is the cost of that cell. Okay. Now I'm saying like that's it. This is the congestion game. Okay. So the available strategies, you know, so again, the available strategy is like if I choose A and I'm the column player, I have to use these 2. If I choose B, I have to use these 2, and for the column player that way. And I claim that like okay, so this is clearly so the costs are steadily increasing. Okay, as you increase the load, everything goes from 0 to something positive. Okay, number 1. Number 2 is like they're trivially linear because there are only 2 points. Okay, so this is like a linear. So it's an affine. Sorry, as to say, it's an affine congestion game, and the price of anarchy is infinity. right? How is this possible? Can someone tell me? What's going on here?
Sorry, what's the question?
Okay, so I have a claim here, and I say that the pure class of anarchy of a fine congestion game is infinity. Okay, and I'm saying like how can we ameliorate this with the results by Christodoulou and Koutsoukias and Ralph Carden of the 5/2? How can this both be right? Yes.
Isn't like approximation going to do without?
No, no approximation whatsoever. This is a perfectly valid, affine congestion game.
But just to be clear, I mean,
Yes.
these functions take two possible arguments as input.
Yes.
They all start at 0 and go somewhere. Why are they not linear?
They are.
What do you mean by affine? I mean, like W is not the input to any of these functions, right? They go from, you mean like at 1, they're 0 at 1. That's what you mean?
Yes.
I see, got it.
Yes.
They're like kind of like with 0, they're kind of like Rayleigh functions.
But they don't have to be okay. Just put everything at epsilon. Raise everything by epsilon. Okay. Let's not talk about Lelouch here. It's like normal form. Please. I don't want to go crazy, All right. So here is epsilon. Here's something like strictly larger than epsilon. Okay. 2 points increasing. Okay. It's affine. How can this both be right? The what? Correct. The intercept is negative. Let's revisit this assumption again. All right. So this assumption here, alpha x plus beta, again, about the cost function. And of course, alpha increasing is very natural. But I want to claim is that like, I don't feel that beta being positive, not negative, is such a universal assumption. So let me try to go over this again. So here's the thing. First of all, how do you even test 2 minutes? How do you even test that beta is 0? Beta is non-negative. Cost at 0 is not defined. This is not something you can measure on any machine. Okay. The cost is only defined for load 1, 2, 3, 4, 5, and so on and so forth. Okay. So even if somebody were to give you Oracle access, this beta greater than or equal to 0 is equivalent to 2 times the cost of Lado 1 is greater than or equal than cost at 2. Okay. And my question to you is why 2? Why not 3? Why not 100? And I'm saying so like, and actually you can imagine, okay, like let me give you an example. Like I think you can create reasonable examples that have this property. Okay, here's a trivial one. Okay, think of a printer. Okay, a printer that before somehow when it prints the last page, it preloads like paper and whatever the printer needs to do for the first page. Okay, as a result, the cost of printing the first page would be smaller because it has already done the pre-booting. Okay, such like anything that's sort of like, you know, any server that's sort of like preload resources could very well disqualify this assumption. And to be honest, I don't see any special reason why 2 feels like an arbitrary constant, but it's necessary. It's necessary for 5/2. If you remove this assumption, you say like, okay, all I'm asking is the function to be increasing and everywhere positive. Pure pairs of finite is infinite. Okay, that's it. And of course, this immediately propagates to any polynomial function. Take any polynomial function again. Now I'm saying like, okay, you use right. So cost functions, you know, in practice, they're not really done by hand. You take multiple noisy measurements, and you do some linear or polynomial regression, do some like maximum likelihood estimator and so forth to try to infer them. Okay. And now I'm saying like, okay, what happens if some of these constants, the non-leading ones, which have high uncertainty, are negative? Why is this impossible? Okay. Well, if they are negative, then we know nothing. Actually, nothing holds, nothing persists. Like price of finity is infinite. That's it. So I'm done. Okay. But what I'm pointing out here is that, like, look, like I think we don't need to run and say, like, look, I really think that in this semester we should not be thinking just about AI and reinforcement learning. Like I think there are some very valid, very interesting questions in normal form games. And I think as we work together, putting all of our skills, like there's a lot of mathematical technology in the area of like lambda mu robustness and smoothness, like really, really powerful ideas. Okay. And I think the combinations of this in dynamical systems will only give us like more power. Okay. And to be honest, I'm kind of excited about these things. They give us a new challenge to work on. Okay. So, all right. That's it for me. Thank you for your attention.
We have time for one question. If there's a question from the audience.
Okay. We'll have time tomorrow as well. Thank you.
Thank you, sir.